Hello everyone, and in this video we're going to be talking about the basics of search. We're not going to be focusing entirely on the path planning problem. We're going to look at the more general definition of what search can do, because it is a very general tool that can be used to solve a lot of different problems and is used this way. Now to start off, we have this search problem, and the search problem is to find the sequence of actions that transform the initial state to the goal state. And this is a very general definition that can be applied to a lot of problems. Problems that I have used search in before are chess, autonomous driving, class scheduling, etc. There are lots of different ways you can use search. So our state is going to be that generic definition of state, and I think I finally found a definition I like, which is a unique configuration of the relevant facts about the world. So this could be the XY position of our robot on some plane. It could also be what is the weather today. These are all those general definitions of state. We also have some goal, which is a specific state that we want to reach. And we have actions. What are the things that we can do? We can talk to people, we can move our robot, we can drive our wheels, whatever it might be for our specific search problem. Now there are a couple attributes about search problems. So we have things like observability. So this is, can I see the entire state space? And when it comes to observability, you can either have fully observable, where you can see everything, or partial observability, where you can only see small parts of it. So a great example of that is if I have a car, and I'm driving down the highway, and there's a giant semi-truck in front of me. How much room do I want to leave between the semi and myself? Usually you want to leave a little bit more room than some car you could see over, because you can't see if someone hits their brakes way up here. You really can't see what's happening beyond the truck because it's so big. This is what we mean by partial observability. Things that might impact your decision making, you can't see. We can also have single agent systems or multi-agent systems. Obviously, multi-agent systems get progressively more complex. We also have deterministic versus stochastic, and remember, stochastic just means our random noise. And deterministic means that there is no random noise. So a great example of this is when you're playing chess, your actions are deterministic because when you move a piece to a location, there isn't some probability that it's going to end up in another location. It always ends up exactly where you mean it to end up. Stochasticity is more like when we have a robot driving around. We try to go forward 1 meter and end up going a little bit farther forward than we meant to. There's also episodic or sequential environments, so things where we only play a single game of it, or where you are repetitively doing the same thing over and over again. A lot of the things we're going to be looking at are sequential. We also have discrete versus continuous, we talked a lot about before. So if we're looking at the game of chess, chess is fully observable because we can see the location of all the pieces. There's nothing we don't know about with respect to our state. It is a multi-agent system because there's another player. It is deterministic. Actions will always give the same result. I'm not going to try to move my piece to e5 and end up accidentally at e4. And it is sequential because we're iteratively playing this game over and over again. What we did last time makes a difference in the future. Now it is semi-static because pieces can move when the other player moves. Usually when you talk about static, you're saying that things never change at all. It is discrete because the pieces can only be in certain locations. So next we have driving, which is partially observable because we can only see certain parts of the state. It is a multi-agent system because there's other cars driving around. It's stochastic because there's going to be some noise in our actuators as well as our sensor readings. It's sequential because we're driving continuously. We're not doing a single instance of driving and then never doing it again. It's dynamic because the world around us can move based on things other than just other players. Like the wind can push over a tree or a storm can happen. This isn't under the control of another player like it was in the chess game, so it's dynamic. And it's continuous. We have this complete set of states that you cannot discretize that very easily. There are also things like industrial robotics, which is partially observable. It's a single agent system. It's stochastic. It's episodic. You only do this a single time. You're doing that single action. It's semi-static because things can move around you, but usually you can think of it as static. The world should be in the same location for the most part. And it's continuous. So the different teams have a little bit different definitions if we were talking about search. This is what I would say. So I would say that RoboNav and RoboRacing are partially observable, while RoboCup is fully observable. And this is really because RoboCup has that camera overhead of the field that gives you an absolute position on everyone in the field. Now there is a little bit of delay, and there's a couple of quibbles back and forth here, but I would say it's more fully observable than partially observable. But RoboCup has some additional complexity in the fact that it is a multi-agent system versus a single-agent system. Usually single-agent systems are a lot easier. Now, the other thing that's really important is that RoboCup has a more dynamic environment. Because you have these players moving around, things are constantly changing, while the IGBC RoboRacing, for the most part, except for their new competition, would be dynamic. So I guess RoboRacing is actually dynamic here, and both are in the continuous space. So as you can see, when RoboJackets does practical applications of robotics, things tend to be more like driving, where things are partially observable, multi-agent, stochastic, sequential, dynamic, and continuous, rather than a really easy case, which would be fully observable, a single agent system, which is deterministic, which is episodic, with a static environment and discrete state. So let's look at the path planning problem and how we define our state. Now, the definition of state is really important, and we're about to see why. So this is the bus map going across campus, and you have these different stops all along. Now, there's multiple ways we can look at this. We could say that our state is equal to our location. So this would be a continuous position in x, y, let's say. And this is going to give us a large number of states. We could also say that our state and our action is the bus driving. Now, as you can see, this has a large number of states. We have a continuous both state space and action space, and this will essentially end up with an infinite graph. But is there a different way we can look at this state problem and get a much easier solution? Which is what you tend to do when you're actually looking at this bus map. What you're trying to do mostly is going from one bus stop to another bus stop. And this is because it's a reasonable number of states to actually compute this path over. So if we use our state as our bus stop and our action as going to the next bus stop, we end up with a much smaller state space. Before we had essentially an infinite state space with our location, and now we have what, 20 bus stops? So that's 20 states, and our action is moving to the next one along this line. So this would be connected here, and this would also be connected back, but some of these are only connected in one way. So this greatly reduces the number of things that we have to compute, and would actually be pretty reasonable to just brute force search over this and look at every possible path that you could have in this graph and figure out what the best option would be. So while brute force is computable for this action definition, it is completely impractical for the other one. So this is kind of the idea of search. How you define your state space and how you define your action space is really, really critical. So in summary, search is a general approach that can be applied to a lot of problems, and different environments have different complexities that we have to worry about. And your state and action space matters. There are ways you can define your state and action space so that it becomes completely computationally intractable, and there are also ways where you can define your state and action space that it becomes trivial to solve. It all depends on your state and action space, and you need to choose one that makes sense given the problem that you have. The more states you have, the closer you are to the continuous solution, but also the more states you have to search over. So what you want is some action and state definition that gives you a good enough solution while also keeping the number of states very low.